Okay, we can start now. All right. Hello, everybody. Welcome to the spring semester's final talk for the TIES webinar series. It's my great honor to introduce you to Dr. Peter Dueben. He is the head of Earth System Modeling section at European Center for Medium Range Forecasts, developing one of the world's leading global weather forecast model. Before, he was the AI and machine learning coordinator at ECMWF and University Research Fellowship of the Royal Society, performing research towards the use of machine learning, high performance computing, and reduced numerical precision in weather and climate simulations. Peter is coordinator of the Maelstrom Euro HPC joint undertaking project that is implementing a software hardware co design cycle to optimize performance and quality of machine learning applications in the area of weather and climate science. I would request everybody to just mute their mics during the talk and ask any questions toward the end of the presentation. And with that, the floor is yours, Dr. Dopan. Thank you very much.
Perfect. Thanks a lot for inviting me. I'm going to talk about digital twins of the Earth system and also what I call the digital revolution of Earth system sciences. I'm coming from the European Center for Medium Range Weather Forecast, which is quite a mouthful. But I have one slide basically to give you a bit of an impression of who we are and what we do. So we are a research center. But we also provide operational weather predictions. So we basically are 24/7 operational weather center. And in particular, we're kind of focusing on global weather predictions and also focusing on kind of a couple of days into the future. So that's what we call medium range, but also all the way to monthly and seasonal forecasts in principle. And we have a lot of member states that you can see on the right side, all the member states that we have in our community. And you will see that they're kind of mostly focused around Europe. We're based in 3 different countries by now, in Reading, in the UK, in Bologna in Italy, and Bonn in Germany. As we're doing operational weather predictions, we have supercomputers, and we also are the home institute, if you want, of the so-called integrated forecast system, the so-called IFS, which a lot of people will know as a kind of one of the leading global weather prediction systems. And we, since recently, also developed what we call the artificial intelligence forecast system. So like a machine learning hybrid to kind of also kind of provide predictions. And some of you may also know us from ERA 5. So it's a reanalysis product that's kind of quite well known in the community. That's who we are. And since we're doing kind of global weather predictions, we have to think about like what's happening in Earth system modeling, obviously. And I think I only recently have introduced this slide into my slide deck. And it's fair to say that at the moment, Earth system modeling really is kind of experiencing quite disruptive changes in principle in the community. And this is kind of offering great opportunities, but also obviously great challenges. And I normally don't provide this kind of buzzword slide at the beginning, but I think it's really fair to say that at the moment, we have kind of quite a specific time period in our domain and kind of in Earth system modeling that will kind of come with a lot of changes in principle. And I'm going to talk about this a little bit in this talk. So why is Earth system modeling difficult in the first place? So what do we do actually for Earth system modeling? And obviously, if we want to do Earth system modeling, the first thing that we need to do is to kind of represent the Earth system. So you have the figure of the Earth system on the left, and you kind of see all of the difficulties that it brings along. One of them is that it's extremely big. So the Earth is kind of quite a big thing. So therefore, if you want to model something on it, you're always struggling to kind of find enough compute power to actually have high enough resolution in your systems. So in operational weather predictions, we typically work with something like 10-kilometer resolution, and this means that a lot of the important processes, like for example, individual clouds, are not resolved properly. So that's one challenge. The other challenge is that the whole system is obviously a fluid dynamic system. So you basically have nonlinear differential equations, and you also have chaotic motions. So you basically have an exponential increase in errors. You also have a multi-component system. So you have atmosphere, ocean, land surface, sea ice, land ice, atmosphere chemistry, cloud physics, and all these kind of components interacting with each other. And therefore, those Earth system models are very complex with kind of up to 1 million lines of code, basically. And Yeah, it's also kind of all the interactions to get them right is also very difficult. So in principle, the Earth system is not an easy and nice thing to kind of look into in terms of modeling. On the other hand, we have a lot of information about the Earth system. So we have, for example, plenty of observations coming in every day. At ECMWF, you typically receive something like 800 million observations per day. And they're coming from all sorts of different sources. So you have satellites, you have planes, you have ships, you have ground measurements, you have radars into the sky and weather balloons and all these kind of things. And that's fantastic because we basically get a good impression about the Earth, but it's also difficult because we have a lot of different sources that come with very different properties and so on. And also, most of the observations are actually coming in the northern hemisphere because the southern hemisphere has less observations taken, and so on and so forth. So there are also difficulties here. So that's the difficult piece that we are kind of looking into. And I'm going to talk you now about through 3 different revolutions that we had in Earth system modeling in the last couple of decades. And the first one is the so-called quiet revolution. And what I brought you here is a graph that is basically kind of showing you the improvements of forecast accuracy in weather predictions over time. So the x-axis is basically time in decades or in years and kind of over a couple of decades. And the y-axis is really kind of a quantity that basically shows you like how the weather forecasts are improving as an anomaly correlation of what we call geopotential height. And what you see is basically the higher the better. And you see that kind of all the graphs are going up from the bottom left to the top right. The different colors are the different forecast lead times. So blue is, for example, a 3-day predictions, red is a 5-day prediction, and green is a 7-day prediction. And you can see basically how global weather predictions really improved over time consistently. And this is basically about like a consistent investment as well into the field, but it's also about like better observations in principle and also better ways of using those observations with data assimilation, better high performance computers that then kind of resulted into kind of better resolution and also better numerical algorithms of our model simulations. So a lot of factors basically led to this kind of steady increase of quality. And as I said before, this is kind of called the quiet revolution, mainly because basically that's happened over the decades and people didn't really realize that we kind of actually really made a lot of improvements in weather predictions in principle, but yet we did, and it's kind of something to really recognize. However, at some point we're kind of hitting the limit of the quiet revolution, and to kind of show you this is basically brought you the figure now on the left again. So the plot here shows you the different peak performance that we were using for the supercomputers at ECMWF in time. So we started with something like megaflops a couple of decades ago, and now we went all the way. I think we are now at 40 petaflops. So this is our old computer, and the new computer has now 40 petaflops. So you basically go from the 80s with megaflops all the way to kind of petaflops now. And the y-axis, you see the resolution that we were able to work with on the different supercomputers. So as we kind of increased our compute power, we could increase resolution. And this meant that we kind of could resolve more of the important processes of the Earth system that are kind of diagnosed here on the diagonal. And now, as we kind of reach the exascale, we really hope that we can go to a resolution level of something like 1 kilometer, because we are quite certain that this 1 kilometer resolution will actually allow us to kind of really push the quality of our weather and climate predictions even further, because we will be able to resolve like explicit thunderstorms and stuff like this, and is kind of very important for the energy cycle. However, on the top, you see what we call the sustained performance that we achieved on the same machines. So the peak performance is what you can get theoretically out of your supercomputer. The sustained performance is what you get for your specific application in terms of the number of floating point operations per second. And you will see that we started with something like a factor of 2 at the beginning, 500 to 200 megaflops, and we went down to something like a couple of percent in the end. And I think now we actually reached the level where we only have a fraction of a percentage or something like this in terms of the peak performance to sustained performance. And this means that we're not actually doing well in terms of making big use of our machines. So we actually kind of struggling to kind of get good, make efficient use of nowadays supercomputers. And to kind of tackle this, we basically said that we need what we call the digital revolution. And this basically means that we kind of have now to rewrite our model simulations and our model systems in a way that we can actually kind of really make use of those very powerful new supercomputers. And by this, basically being able to kind of push to this 1 kilometer resolution level. But that's kind of quite a big step for us, because we have a million lines of code to kind of run them on GPUs, for example, is tricky. We also need to think about how to let the domain scientists kind of work with some sort of code that is easy to work with, but on the other hand, to have a portable and scalable code that the computer scientists can deal with. And this is kind of really was assumed to kind of be a big thing and the big basically investment needed. And we were quite lucky because we are actually able to kind of get such an investment for the digital revolution in Europe. And in particular, we went for the so-called Destination Earth project, which is a fairly large European Union project, also called Destiny. And the idea here is that we kind of now really push our model simulations that we have to the kilometer scale. And by this, we will increase the realism of our simulations quite drastically. And then we will reach a level that we basically kind of will be able to call our models digital twins of the Earth. So the idea is that we kind of get so realistic in our features that it will not be possible for even for domain scientists to distinguish between a model simulation and the real observations. And I've shown you this picture before here, but I haven't really told you that on one side we actually have a simulation at 1 kilometer, and on the other hand we have the observation data. And even the domain scientists could normally not tell you which one is which. So we're getting there in a sense that we really have like a digital representation of the Earth system that is really kind of extremely realistic. And this also allows us now to kind of really treat this as a kind of digital laboratory. So if we want to kind of make tests, for example, what's happening if the Amazon region would kind of just turn into a savanna, and we could do this in our model, and we could actually trust the results in a sense of the realism of the solution. So we can kind of use this basically as a digital laboratory, which is kind of what we want to do with, in principle, digital twins. Obviously, digital twins is one of those buzzwords, but I think in this case, it's kind of really valuable. Another thing that we wanted to do with Destination Earth is also to kind of make the whole thing more interactive. So what's typically happening in Earth system modeling is that you have an Earth system model observation kind of happening at some point, and then people are working on this, and they produce then data, and the data is kind of going to be used by the impact sector. And the impact sector is then basically distributing, for example, weather forecasts or energy prediction and stuff like this to the users. And we want to get away from this in a sense that we want to make the whole process more interactive. So what we actually want to end up with is a system where we basically have kind of integrated the whole thing. So it's kind of now going two ways, that the impact sector can also kind of make suggestions for the model simulations to be run. And also the users will kind of be brought much closer to the whole engine, if you want, in the sense that they can also basically run the impact models, for example, within the high resolution simulations that are run globally and a bit more centrally. So there should be more interactivity, and also the quality of those simulations should really change in a sense, in particular, to go towards high resolution and kilometer scale simulations. So that's kind of what we do with Destination Earth, and we're actually doing quite well. Destination Earth is like 2 years into the project now and quite successful. So we now basically can run those kilometer simulations on kind of fairly easily on our supercomputers. We also run them daily for weather predictions, and we can also run the kilometer scale models now like really for decades. So we can do climate type simulations, and this is really helping us to kind of increase the realism of our simulations. So for example, on the top left here, you see the Arctic, and you see how kind of sea ice cracks are developing on the sea ice, which is kind of visible now because we have the high resolution. And this is kind of really changing a little bit how the energy is kind of distributed between the atmosphere and the ocean. So quite important. So we were kind of quite good at actually improving the local scale with those kilometer scale simulations. The plot on the left is basically showing you how kind of the global interactions are happening. So you can kind of see the flimmering here, which is kind of coming from the daily cycle. And you see how, for example, convective cells in Africa will kind of impact then on the larger scale and kind of impact on the whole dynamics of the Earth system. So also like we're hoping to get like a better global scale in principle. And on the right side, you see an example of the coupling idea as well. So I told you that we have all the different components in our Earth system. And here you basically see how wind gusts are interacting with the topography. And you kind of really see the amount of detail that you get for kind of topographic leeways and so on and so forth. So basically, we get really a lot of realism as well in the coupling stage. So those kilometer scale models are there, and they are useful. And they are also now becoming available in a sense that like the community can actually trigger those simulations and make them useful for them. That's all great and good. That's kind of happening. So basically Destination Earth really realized the digital revolution for us. So we had kind of quite a big of demand in terms of compute power, and Destination Earth really helped us to kind of push this forward. We see kind of just to make this digital twin impact also like a bit more visible as well as you kind of go to high resolution. You can also resolve like in particular like storms and what we call a medicane. So it's kind of like a tropical cyclone, but it's happening over the Mediterranean Sea. And those storms are a little bit smaller than tropical cyclones. So therefore, they're kind of quite difficult to catch with kind of standard models. And as you kind of see, as you go from left to right here, you increase resolution from 29 to 9 kilometer to the 4.5 kilometer, and you're really kind of getting closer and closer towards the observations that you get for wind speed for those medicane simulations. And on the bottom line, it's quite a busy plot, and you don't need to understand all the details. But what you basically see here is the wave height that you have in the model simulation on the x-axis, and then the observation on the y-axis. And basically, in a perfect model, you want to be on the diagonal, and you're kind of doing fairly well for the lower wave heights. But for the high wave heights, you really kind of see that this line is kind of approaching the diagonal as you kind of increase resolution to the right. And so again, it's kind of really for those extreme events, we're kind of really happy to have those kilometer scale simulations because they really bring a better representation of reality. So this is basically just to show you that these simulations are also running for a very long time. I don't want to go into really detail, but we really kind of get kind of quite good behavior both on the local scale, for example, when representing city level kind of features, but also on the global scale, for example, when we think about like global circulation patterns like the Madden-Julian oscillations and others. So this is all good and well for the conventional model. So we're getting there in terms of digital twins via destination Earth. But that's only part of the story nowadays. The other part is machine learning, as you can probably think already. So machine learning is everywhere, and it didn't stop for system modeling. So basically what happened was that we looked into a lot of machine learning applications ever since something like 2018. So we basically were exploring kind of the area of machine learning for weather and climate predictions in principle. And a lot of the weather centers, they kind of try to combine machine learning kind of tasks with their conventional models and try to improve the conventional model itself. So we've published a paper in 2018 where we basically produced the first weather forecast with a machine learning model, basically. But this was kind of more like a toy project for us. And so back then we really didn't want to kind of change the world. We just wanted to understand what machine learning can and cannot do. And we thought that kind of building a global weather prediction system would actually kind of be quite a nice application. And 2 years later, we kind of defined what we call a benchmark data set. So we basically defined a task that everyone should learn, basically, if they wanted to kind of do this study of a global weather prediction model based on machine learning. And a lot of people jumped on the train in that sense, and a lot of people started the development, and in particular also a lot of like technology companies jumped on the train and kind of started to develop like global machine learning models. So we have like in 2022, it was a busy year here. So NVIDIA kind of published a paper basically where they did global modeling. Then also Huawei published a paper. Then December, like Christmas 2022, DeepMind and GraphCast published a paper. Then Microsoft and so on and so forth. And basically these models were really kind of overtaking themselves. They were really kind of producing very good predictions. And the speed of development was really kind of quite astonishing in 2022. So what we ended up with was this figure on the left, which is quite an iconic figure. It's really boring if you kind of from the way the figure is done, but for someone who's working in system modeling, it's kind of really a seminal figure in a sense. What you see here is it's kind of copied from the DeepMind paper that came out Christmas 2022, and what you see here is a forecast lead time on the x-axis. And you see different fields on the y-axis and different vertical levels and pressure, for example, but it doesn't really, you don't need to go into detail at all. But whenever this figure is blue, it basically means that the pure machine learning forecast from GraphCast is performing better than our conventional weather prediction system at ECMWF for deterministic forecasts. So this figure basically tells you, like, on a statistical sense, the machine learning models are better than conventional models, and that's quite something, right? I mean, if you, I'm leading a section at ECMWF with like more than 40 people working on conventional models, and suddenly Google comes ahead and says, like, we're doing better than you. So it was kind of quite something to think in. And we try to understand what these models actually do. So why are they so good? And are they actually so good? Just because they're good scores, it doesn't necessarily mean that they're very physical, right? So we had to look into these questions in 2023. We had our doubts. For example, it's clear that those models typically kind of tend to smooth out as you kind of go to a longer forecast lead time. And this is because they were trained to kind of reduce the root mean square errors for like longer term predictions. And this means that you kind of get double penalty if you kind of conserve like sharp gradients and these kind of things. So we knew that the behavior was kind of as kind of shown here in the figure from a Keisler paper, where you have the reference on the left, the era 5 reanalysis data kind of progressing in time from top to bottom. And you see that the features obviously stay sharp as the Earth is kind of progressing, because there's no reason why the Earth system should just change the dynamics. But as you kind of look into the machine learning models, you see that they're smearing out. So kind of from top to bottom, you see that the machine learning model is kind of losing fine scale features. And we know that this is kind of unphysical. So these models were kind of thought of basically being kind of unphysical emulators to some extent. So in 2023, we looked into the questions whether these kind of smearing out of small scale features can be avoided, whether these models can actually also be used to learn uncertainties. The question whether these models can faithfully represent extreme events, for example, which is unclear, because if you have like a 40 years training data set from the atmosphere, and then you want to kind of predict an event that is only happening every 100 years, it's difficult to trust those models, and we need to kind of show and see whether the models can actually be trusted. And we also wanted to know whether data assimilation is also something that can be done with it. So at the moment, these training data sets, the era 5 training data set is kind of based on observations and on conventional models. So the machine learning models is still using basically information from conventional models. But the question was whether data assimilation kind of brings in observations and the model simulation itself together to generate initial conditions can also be done with machine learning, because then you kind of could replace everything with machine learning. So these were the questions in 2023, and we looked into them. And what we've done is we kind of took one of those models in detail, and we're running it in-house, and then kind of started to look into the results with our forecast, with our meteorologists, and kind of try to understand the nitty-gritty details of what's happening. And we submitted a paper in July where we basically kind of summarized that the results were actually really promising for the machine learning model. So the skill was comparable for global metrics and extreme events. And also in comparison to observations, the models performed actually surprisingly well. So in general, these models are not bad. What we've done next is we basically took 3 of those models in September, and we kind of published the results from those models on a daily basis on our webpage, and we still do. And this was basically to kind of show the community, or to give the community the chance to look into those weather prediction and to feed back to us whether they're useful or not. And again, I think we received fairly positive feedback. And then the next step for us was kind of to also build our own global weather prediction system with machine learning. And in October, we finally revealed the alpha version of the so-called AIFS, the Artificial Intelligence Forecast System. And back then, we still had kind of a system that wasn't kind of up to the challenge in comparison to models like GraphCast. But I think nowadays it's fair to say that we actually kind of really are also playing in the leagues with the big guys in terms of like how the model quality for our model system is performing. So we are really have seen that this is kind of important to look into, and we were getting there in terms of model quality as well. So what does it mean in terms of like if you compare the quiet revolution now with the digital revolution? So this is a figure I've showed you before about like, how forecast quality developed over time. And if you now plot the same thing, the anomaly correlation basically for the machine learning model, you will see that there's kind of quite a drastic jump in terms of the quality. So the dark red line here is now the AIFS. And the red line is kind of the quiet revolution developing over 20 years. And you see there's quite a step change. So it's really quite significant how good those machine learning models are in principle. And this is also still not including, for example, that you can, in a machine learning model, you can also bring in more information, for example, from synoptic observations. So from weather station, basically, that would still like improve this kind of this delta and probably even more so. So a lot is happening here. I asked you some questions for the 2023 setting, and kind of we tried to answer them, and I'm just going to go through those different questions now one-on-one to kind of see where we are at this stage now. The two of those questions were whether the models can actually kind of avoid the smearing out effect over with forecast lead time, and also whether the models can represent uncertainty. And this is a figure from another Christmas present from Google DeepMind, which they published in 2023 now at Christmas. And what you see here is now you have the truth on the left side, and you have different models at different kind of forecast lead time after 12 hours and 10 days. And so you would basically want all the figures to look like the figure on the left. And what you see is you, with the graph cast, with the old model, you basically were smearing out quite a lot from 12 hours to 10 days. And so you were losing small scale structures, but now they have built an ensemble system. And with the ensemble system, they can generate different samples. And those samples are actually not smearing out that much anymore. This is what you expect because you basically have a specific way of training those ensembles, and you kind of have specific loss functions that you look into. But this basically means that you can represent uncertainties, and also you can avoid the smearing out of the structures. And you can also see basically in ensemble scores that these models are now really competitive in ensemble predictions with the conventional models. So these models are really quite useful. So the answer is yes to the two questions above. Then the next question was basically whether machine learning can represent extreme events as well, and also whether the model is kind of physically consistent. So what we've done is we looked into how these machine learning models developed over time over the last kind of couple of months, and we kind of on a daily basis compare like the AIFS with the IFS, and we kind of looking really for like unphysical behavior and things that the model cannot really do very well. And we don't typically see this. So normally AFS and IFS are fairly similar in quality. You get sometimes situations like, for example, the one that I'm showing here, where the AIFS is actually performing much better than the IFS. So you have the control simulation and the operational prediction on the left side. You see an error pattern over the US, which is kind of quite significant. So this was kind of not a very good forecast for the IFS. But in the AIFS, in the machine learning model, you actually kind of get much lower errors. And that's even true for kind of fairly extreme precipitation events, for example, as well. So these models are performing also well for the extremes, and also they're fairly physically consistent as well. So yes, can the models do data assimilation? That was also like a big question. Why would we not think that they can do this? First of all, it's much more tricky because for the forecast model training, we basically have a very good data set, the ERA5, where you have like 40 years of the atmosphere dynamics in a very consistent, full, nice, evolving data archive system where you can also kind of read in the data fairly easily. We have a benchmark problem with WeatherBench. But for observations, this is not true. For observations, it's kind of a lot of work because you need to collect all these observational data sets and kind of bring them into a nice form. And also, it's very difficult to compare them and different approaches. Then also, the more you go back in time, and if you're just learning from observations, the less observations you have. So if you train from the 70s, for example, you don't really know whether the system actually still has kind of enough information from the observations that you are using. And this basically means that you're generating a huge null space. So there will be areas in the globe, for example, in the southern hemisphere, where you have hardly any observations, and you need to kind of generate a lot of information that is not there. And then finally, also satellites, for example, that come and go. So if a satellite is living, for example, for 5 years, and you need 2 years of training data to make it useful, then it's kind of you're losing 2 out of the 5 years for your system. So it's also kind of a question what you do about like new satellite products and new observational products in comparison. Why would it work? Because we know that for so-called observation operator, it's working naturally. So that's basically a system where you kind of learn the mapping between observations and the model. And that's kind of something, it's really a statistical problem. And it's kind of something where really machine learning can help you very easily. You also know that all the individual steps of the conventional data simulations can be done with machine learning in principle. So why wouldn't you be able to do the whole thing? And then finally, we also know that generative models is really good at kind of generating kind of gap information, for example. So I told you in the last slide that we can generate like ensembles, and the same way we can probably also kind of fill this null space. And finally, a lot of things were tested by very skeptical scientists and turned out to actually be very kind of easy to do for machine learning. So it's also that the machine learning has this kind of benefit of the doubt in the sense that it's difficult to not believe in machine learning in some way. And what we see is this. So this is a paper I was involved in where we basically kind of try to we take atmospheric information of the atmosphere, and then we kind of basically just take point data in this kind of three-dimensional fields, and then we try to regenerate the whole atmospheric system from this point data using a diffusion network. And what we see is basically the more columns we have, so the more observations we take from left to right, the brighter the color will be. So this basically means that the error is reducing, which you expect. And if you then compare the error against the GraphCast error at like 6-hour lead time, you see that the initial conditions is kind of fairly good in the sense that we're really producing kind of quite good analysis products in principle. And there's also other papers coming out, like for example, the Aardvark weather model, where they really show that data assimilation is indeed possible. So we're almost there with data assimilation as well. So is this the end of conventional modeling? Is machine learning now taking over everything and we're not going to do anything else? I doubt it. And I kind of brought you back our digital twin, digital revolution slide, where I kind of showed you why kilometer scale modeling is so amazing. And I think I want to stress this point here that all these kind of features that I showed you that are so great about kilometer scale modeling, they can't be done yet by machine learning. So you can't really do the local scale with kind of cracks and CIs. You will really have to think about whether you have enough information about the system, for example, to ever learn this. You can't really make the interactions between local and global scale so dynamic and understandable that you kind of can learn the bottom left if you want. On the right, the coupling is also not still work in progress and so on. I'm not saying it's not possible, but basically I'm saying that there's a lot of delta basically still between a lot of the questions we are interested in and between the conventional models and the machine learning models. And also, normally we don't compare, for example, a post-processed machine learning model against the conventional machine learning model. So we also have to be very careful that we're not kind of comparing that we are comparing apples with apples in terms of model quality. It's also true that these machine learning models wouldn't even know what's happening if, for example, suddenly a volcano would kind of erupt and there would be a lot of aerosols kind of coming into the stratosphere and so on. The machine learning model would just not know how to do this. What is an aerosol in the first place, basically, right? So there are a lot of questions that these models can't answer as well. So basically, my point is that it's not kind of either or. We basically will kind of come into a system where we have conventional models and machine learning models next to each other at the same time. But having said this, it's also fair to say that most of the weather predictions that will actually be used by the users. So if any of you is kind of taking up their smartphone in like 2 years from now and kind of looking into weather prediction, it's quite likely, very likely that this kind of weather prediction is coming from a machine learning model. So basically, a lot of things are going to happen in terms of how the machine learning forecasts are actually kind of influencing numerical weather predictions in the future. Okay, there's also this hybrid world. So you can also not just go all in to kind of the full machine learning model or the full conventional model. You can also kind of combine the two worlds in one way or the other. And there's a scale here. So if you go from 100% conventional modeling on the left and to all the way to 100% machine learning model on the right, you can basically have a different kind of percentage in the mix if you want. So you can do basically things like parameterization emulation, where you basically just kind of emulate parts of the conventional model. So it's kind of very much like conventional modeling. You can do things like post-processing, that you just take machine learning, for example, and you kind of just post-process the result from the conventional model. You can do bias correction with reconstrained Fodivar and very detailed, but in basically the essence is that you kind of learn forecast errors within your data simulation system and then correct for them. And there are different kind of notions of doing this. You can also couple a machine learning model with a conventional model. So for example, you could think about coupling a machine learned atmosphere model with a conventional ocean model and these kind of things. And then also you can basically try to learn the whole physics. So basically just take a fluid dynamical component, for example, and then use a machine learning model to just kind of learn all the things that are uncertain in the model simulation. And this could, for example, be all the model physics like clouds and cloud representation and so on that are typically parameterized. And it's very interesting to look into this, and it's kind of quite unclear how this is going to develop in the future. So how much kind of this hybrid machine learning conventional model is going to play a role in this world between machine learning and conventional modeling. But there's one thing to be skeptical about, and this is climate. So the problem with climate simulations in machine learning is that we know that machine learning models cannot extrapolate. So they can basically not kind of look into unseen futures where the underlying data framework is changing. And this is kind of happening in climate change. So as temperature rises, our distribution of the physical fields will change. And therefore, we would need to understand how much the machine learning models will need to extrapolate to actually kind of trust the predictions there. And the problem here is it doesn't really matter too much whether you are 100% machine learned or 10% machine learned. At some point, you basically will need to trust your machine learning model whether it can extrapolate or not. Having said this, there is now a paper that basically looks into hybrid modeling in a quite interesting way of basically kind of combining a fluid dynamical model and a machine learning model by training through the dynamical core of the model, basically. And I think this is really a nice approach. And what they get in the end are basically simulations where they can perform what we call AMIP simulations. So AMIP simulations are fairly similar to climate simulations. With the one big difference is that you don't really think about CO2 concentration, but you really think about like surface temperature of the ocean. So you just assume that you know how the ocean is developed in the next 20 years, and then you run an AMIP simulation to kind of like to see how the atmosphere is responding. So it's not a climate simulation because it doesn't have CO2. It's not a climate simulation because it doesn't really kind of have an ocean, which is very essential for climate. But it's kind of just looking into how the atmosphere is evolving. And what we see in this paper here is that we basically get like extremely good results in terms of the biases are small, the tropical cyclones are right, the response to like a warming, the surface temperature is correct and stuff like this. So it's kind of quite interesting to see that this model simulation actually is really performing quite well, even though it's a more or less free running machine learning model for the atmosphere. And this kind of basically indicates that climate model simulations may also be possible with machine learning. To do this, what we basically need, the reasons why climate model simulations should not work with machine learning is because machine learning models can't really extrapolate. They don't really even know what CO2 is. You also need a model that's kind of representing all the different components of the Earth system, like ocean, sea ice, land, aerosols. We will need to represent the deep ocean, and we don't have any good data for the deep ocean because the deep ocean has very long time scales and we don't have a lot of observations. So if you have 40 years of the deep ocean and we only have a couple of observations, then this is really not enough to really learn the dynamics of the deep ocean. And it's also a matter of trust in a sense that even if we had the perfect machine learning model and we would run it for 80 years, we would still have a bad taste in the mouth in a sense like, is it really trustworthy? Do we really extrapolate this? And there's never going to be a good answer to this question. On the other hand, we can do these AMIP simulations. We can can learn all the components individually. The deep ocean is also difficult for conventional model. The existing models are remarkably robust, for example, for this kind of weather situations in the extremes. The machine learning models will be basically bias-free for the past scenarios, and they will basically be conventional models in almost all the different diagnostics. And therefore, I'm pretty sure there will be climate simulations in one way or the other. So regarding the different components, I'm going to skip the slide a little bit. But basically, we see good results for land modeling with machine learning. We see good results for sea ice modeling with machine learning, and we see good results with ocean modeling and machine learning. So there's no reason why we should not be able to learn those components individually and then bring them together. One more thing that's actually interesting now is as a next step of what's going to happen in the community is that we will probably make the push to what we call foundation models. So what is a foundation model? I wanted to explain with a slide here, but before I do so, I wanted to show you one slide that I used in 2020 to kind of to show where machine learning is currently used at ECMWF. So that's kind of a 4 years old slide. And what you see is here is you have the operational workflow at ECMWF from observations to data simulation to model simulations to products, and you have all the different application areas where we used machine learning back then. It's a busy slide, don't go into the details, but what you should believe me is basically that we had a lot of different options of how to use machine learning in this workflow. And back then, we basically talked about like a gigabyte of data here and a gigabyte there. But if you really want to if you're really serious about many of those applications, you basically end up with kind of petabytes of data, or at least terabytes, many terabytes of data per box. And basically, this means that you have a lot of compute power that you're kind of wasting on all these different application areas in principle. So the question is, how much can you unify those approaches, and how much can you basically rather train one machine learning tool to kind of beat them all, and not kind of have a lot of different individual machine learning tools for the different applications. And that's what you try to do with the foundation model. You basically try to kind of build a generic tool that can be used in a lot of different application areas. And we have seen some very good example like AppMurap and ClimateX. So there's some progress in the field. And we have now also submitted a fairly big research proposal actually for the European Union, where we also want to look into these foundation modeling for weather and climate. And basically in this proposal, for example, we want to build one big machine learning tool, and that should then be used for a lot of different application areas. And we have, for example, here 22 applications in the one proposal here. And we want basically to kind of build this backbone, this foundation model backbone, and want to use it in a slightly adapted way for all the different applications to basically save compute power and time, but really also kind of to build a tool that is more generic and probably also better in understanding, like, for example, extrapolation problems and these kind of things. So how does it work? Basically, the idea is that you have kind of one general model that kind of works probability as well, and you can basically kind of put in very different data sets, like reanalysis data sets, model data sets, observations, and all these kind of things. And the model is able to kind of cater for all of those inputs. And then you can basically use tail networks, so like specific machine learning solutions in the end. And then you can basically do the different applications you have, like weather forecasting, post-processing, climate projections, and so on and so forth. So that's basically the general idea behind this. And you do this by an approach which is so-called representation learning. So you don't really use a specific problem to kind of learn. You basically, what you do is you have a big set of data sets, and then you kind of try to remove different information, for example, different data sources and stuff like this in the problem description, and then you fill them with machine learning. So you're kind of building more like a generic tool for the problem of like atmospheric dynamics, for example, rather than a generic tool for a very specific application area like weather forecasting. So that's kind of all work in progress. I can't really show you great results yet, but I think this is really also going to make a difference for the community. And in particular, it basically will provide like a very good tool that that's going to be very useful for the scientists. So if you imagine that basically some person wants to look into weather and climate data, and they would basically have all the relevant data sets in the same data system, and kind of could basically feed in all the data sets into a common framework in this foundation model. And there would also be kind of access to federated data and federated computing using a uniform API. This would kind of really give a big boost of productivity for the scientists, because they would basically be able to really make use of it would remove all the work that is needed for like data processing quite significantly. Then imagine that there would be an off-the-shelf foundation model that could basically transform all the data sets into the other. So you could basically take model data and transform it into what looks like observation data and the other way around. And kind of you do basically all these kind of things using this representation learning approach. And then you also have like off-the-shelf tools for specific application areas. So there would, for example, be like a downscaling application over precipitation in the UK. And if you're interested in the precipitation in Texas, you could basically just copy what the other people have been doing from off-the-shelf solutions, and kind of also kind of do your adapt the tool they have to your local data set and be happy with the result. The tool should be scalable and run on laptops and supercomputers. And also they should basically be tested very detailedly in terms of, for example, the quality of results you get in extrapolation into climate science and stuff like this. So you would also get a much better impression about the limits of the tools. To do this, you basically need fairly big programs, and this could be Destination Earth. This could be a project like Earth 2 from NVIDIA. It could be the Earth visualization engine that is kind of really pushed for like global modeling and also kind of global data processing and stuff like this. But we're basically talking about projects that are getting very large, and it's very important that these projects are kind of really also looked at a very big scale. So this is kind of summarizing the progress that we had with machine learning so far. It has been really quite astonishing how much things have changed in the last 2 years. So we are at a stage now that machine learning models can beat deterministic models, ensemble models in terms of conventional modeling, and we can also do like AMIP simulations. The next thing that's going to happen is that we will be able to do data simulation with machine learning. We will basically kind of go to Earth system models that have also ocean, sea ice, and waves and land components. And then I'm pretty sure we will go to climate simulations as well, whether climate modelers like it or not. There will be models doing this. And also we will go towards the foundation modeling in principle. I'm running out of time, so I'm going to skip these slides. One thing that's also interesting to see is kind of how actually the field of weather prediction will evolve in a sense that up to now, basically, weather predictions was always a public entity, like public services were basically provided. And now all these tech companies have started to do machine learning and weather predictions. And the question is like, how does it actually kind of is now changing the way also like weather predictions are done in general? And for example, who is going in the future, who's going to actually perform, for example, weather warnings and these kind of things. So there are a lot of questions here. Also how we do these kind of things in the future. Okay, I'm basically done, and I'm going to leave up the slide here as a kind of a summary of what's basically happening. I think the bottom line is we had 3 different revolutions happening. 2 of them are really fairly recent and ongoing. A lot is changing in our field right now. But in the end, the models will be better and the tools will be easier to use, and also the way how we do supercomputer is going to be easier with those machine learning models, for example. So it's actually kind of quite a positive message, I think, even though people can get scared of machine learning. In principle, those tools are helping, and we will basically be able to get better weather predictions with them. Okay, thanks a lot for your attention.
Thank you. I would request everybody to unmute themselves and give Dr. Peter Dueben a big round of applause. That was a extremely insightful talk, and it has given at least me a lot to think about. I'm sure participants also. With that, I would like to open the floor to questioning. I have one question that I would like to ask. So with machine learning, usually model interpretability and inference is lost. So how important is that loss to the stakeholders of weather prediction models?
Yeah, that's a very good question. I bet if you ask 10 different scientists in my field, you will probably get 8 different answers. In general, we want to understand what a model is doing, and this is quite a high bar. So we would normally not put things into the conventional model if we don't really understand how they work in the detail. However, having said this, the machine learning models don't really allow that. So we don't really understand how an AIFS model is kind of getting to the prediction, and the prediction is good. So we cannot ignore this, right? I mean, even though we would like to have a physical understanding, if the prediction is kind of fairly good, we should still use it. And also, we have one huge advantage in weather predictions in comparison to other domains like computational fluid dynamics in principle, which is we have a lot of data of the past. So we can actually kind of do a lot of tests with our models. We can run like 40 years of weather predictions and see what the model is doing for specific extreme events. If you want to understand like how the model is performing for tropical cyclones, we can just run it for 200 different tropical cyclones and look how it performs. So it's difficult to surprise us to some extent. If the model is kind of looked at for half a year, it's not that we suddenly expect totally strange behavior, for example. So the question is absolutely valid, and there's no good answer to it because the answer is we don't really understand what the models are doing. But on the other hand, it's still we still can't ignore what the model that this is kind of basically giving us a benefit. So far, these models turned out to be much more trustworthy than we actually thought they would be. But yeah, a lot of people don't like them for this reason. No question there.
So from what I understood is that, and you can correct me if I'm wrong. So digital twins and machine learning have this. Uh, they each will influence each other, right? So
Yeah.
digital twins will help the machine learning, and machine learning is going to help digital twins. So, for example, if you want to digital twin, you can have diffusion modeling, and you can create.
Yes.
I mean, so okay, yeah. Does anybody else have questions? You can also type it in chat if you would like. Uh, so So GraphCast is essentially based on GNNs, and
Hmm.
so one of my questions is that as foundation models and these very large scale models that Google or NVIDIA is working on, how does the energy cost of running these models actually come into play and come into picture of the future of what you described?
Yeah, it's a very good question, in particular for climate modeling, right? I mean, you would typically don't want to kind of run a supercomputer and spend megawatts or megawatts for climate simulations and then basically, well, basically also generating climate change if we want with the simulation. So um at the moment, these models are still comparably small in a sense. So we can, those kilometer scale simulations, for example, you can easily run on, I don't know, 400 GPU nodes in parallel and stuff like this. So they are fairly costly. Whereas the machine learning models, you normally talk about a couple of compute nodes run for a week or something like this. So at the moment, the machine learning models are still comparably small. However, this is changing. And the models are getting more complex. The compute cost is going up significantly over time. And as you also say correctly, as you go to foundation models, the compute cost will be at a totally different level than what we have right now. And then the hope is basically that is you can have only train one foundation model and not 50, but you can potentially use the foundation model as a backbone for 50 applications that you then in the end kind of save compute power. However, this has to be shown. There's no this is science, right? We may it may not work in the end. I'm pretty sure it does work, but um I'm fairly clear that machine learning for weather and climate will have a very strong increase in compute power in the future. And the hope is with those foundation models, you would actually kind of basically limit it rather than increase it. But we'll have
Yeah,
to you have to see.
yeah. So there are some comments in the chat.
Yeah. How would you validate digital twins in general and in specific applications? That's yeah, a good question. I mean, a digital twin is a buzzword, right? There's not the one definition in a sense like this is making it a digital twin and this is making it working well. But I think to me it's really um for the questions that we want to look into, we need to be able to trust the model and we need to be able to kind of work with it as if it would be reality, right? So you would want to basically have a tool like, for example, the global simulations, where you know that the precipitation patterns over Africa will change with the global warming, and you would really kind of have a physical representation of then the cloud and the precipitation patterns that are so close to reality that you can also trust them when you kind of make those experiments. And we basically are there with those kilometer scale models. So I'm very optimistic there. But there's not the one definition how to test them. Can you please comment on the validation of digital twin on different scales? Also good question. So this is kind of also about kilometer scale, I guess. And yes, those models have very different kind of behaviors if you want on very local scale and very global scale. In general, I think we're doing well in basically testing them on both sides. So the two plots that I kind of only quickly showed, but kind of removed, were kind of one of them was on the city level, like on the smallest scale of the model, and one of them was basically on NGO, like global patterns. So we basically test them in all sorts of different areas. And we also test them across lead times. So we basically look into a couple of days predictions all the way to kind of yearly or decades predictions to kind of also think about how the model is behaving on different scales.
Karen, you can go ahead and ask.
Yeah.
Yeah. Hi, thanks for the really great talk. So I interact with and teach a lot of undergraduate and graduate students interested in machine learning and climate. And, you talked about how industry is starting to really play a big role in this space, these very large scale projects. So what advice would you give for sort of early career folks who are interested in going there? Should they be like getting a job at Google? What skills should they be learning? Kind of how do you see the future and how could they kind of prepare for like a career doing research in this space?
I think at this stage, the one most important bit is to not be afraid of those techniques, right? In the sense that if you start with machine learning, everything seems to be like a bit alien and a bit difficult and kind of all these buzzwords and stuff like this. But the methods are extremely simple. So it's much more simple to kind of understand what a neural network is doing than to understand what a dynamical model of a sea ice is doing, for example. So I think the one thing is really to get involved and look into online courses, look into kind of online tutorials and play around with Jupyter notebooks and these kind of things and really get going, because it's very simple to kind of probably within 2 days you will be able to train your own image recognition tool and stuff like this. And these are really the success stories in the sense that you really kind of make a lot of ground and make a lot of understanding, and then you learn something about machine learning. There will be careers that don't involve machine learning in the future, but there will be many careers that will involve machine learning in the future. So I would also advise everyone to kind of at least look into it. Don't ignore it and let it be on the side. We have at ECMWF, we have had a number of really kind of also established researchers who kind of thought, oh, this is interesting, I want to look into it, and they're now driving our AIFS model as well, for example. So it's also not that if you haven't done machine learning yet and you're out or something like this. On the contrary, you can still get involved and kind of learn how to build these models and kind of really engage with it. So my number one point would be engage with it, and there's lots of material for training and stuff like this, and it's worth it. It's not too difficult to start, and it's worth it.
All right, great, thank you.
Yeah, there are 2 more questions in the chat by Venkat and Marianne.
Can you comment on land use and land cover change in the digital twin modeling framework? Very good question. In Destination Earth, we're looking actually quite a lot into this, in a sense that if you increase resolution, obviously you also need to change your land use part. If you want to be interactive, the more short scale and the more interactive you want to be, the more you also need to be dynamic in terms of how you, for example, change land cover parts and stuff like this. So it's actually kind of something that you really should consider and that we do. It's also difficult. Machine learning can again play a role here. So for example, we have one paper that we brought out where we basically looked into a mapping procedure from modeling data to satellite data. And by doing this, we could basically then also identify parts where our boundary condition fields in the land surface were actually wrong, because the error patterns was kind of quite significant. So it is an important part. It needs a lot of work. We have people working on it, and it's important. I don't think I have more to say there. Marianne, at a very basic level, there may always be question of, do we want enough the right and sufficient reliable data? Yes, absolutely. I mean, for climate simulation in particular, we don't know whether we have enough data. We may actually never know, in the sense that if we run a model for like 40 years into the future, it will always be a question of trust. So there are a lot of reasons why you shouldn't trust a climate model in machine learning. The thing is, there will be machine learning climate models, and they will perform well for nowadays climate, and they will basically be there. So the community has to decide at some point how much they can trust them or not. Lelis, how do you visualize using machine learning methods to understand the issue of attribution and climate change to extreme events? Good, tough question. I think nowadays, the generation of machine learning model nowadays, I would probably not trust at all in terms of things like attribution and stuff like this. However, things are changing in a sense that, I mean, we are learning more what the models cannot do. We're learning more what the model cannot do. With foundation modeling, for example, we will probably also build tools that are more generic and kind of can extrapolate better, and to some extent. So we may get into a stage where we can also do attribution studies and stuff like this, but not yet. And yeah, again, it's kind of there are good reasons not to trust the machine learning model there.
Thank you, everybody. That was a great discussion. So I can stop recording if anyone doesn't have any questions, and we can still keep the discussion on. So I will stop.